Today we're super excited to have Fran Bagenal, and she's going to talk about from punch cards to WWW, how technology changed the way we did science on Voyager. So I'm very excited. I'm going to pass the floor to you, Fran. And this is a very informal setting. She's going to talk, and I will have plenty of time to discussion. Thank you, Fran.
It's a great pleasure to be with you and to talk about Voyager, the great mission that I have spent much of my career working on. But really, it's sort of fun to spend some time going back and looking at the technology and what has changed. Okay, so let me just check that I've got everything showing. I think we're in good shape.
Everything's showing, look fantastic.
Great. Okay. So before we get started, I do want to advertise. There's a movie called The Farthest, which is a lot of fun. And here's me. I think I was talking about plumes on Triton. Anyway, it's a great movie that you can watch. A lot of it's on YouTube, but you can get it on Netflix. And it tells a lot, not just about the science and the people, but it also talks about how the mission came together, and it does actually talk about the technology as well. So scientists and engineers coming together. I encourage you to watch it. Okay. Now, Voyager, of course, with this beautiful spacecraft with 11 science investigations on it, all sorts of stuff. It was built in the early to mid-70s, being launched in 77. And so it had to use fairly old technology because, that was what was available. It had to be reliable. You can't use the most recent technology. It has to be tested, obviously, before you send it up into space. I'll mention the radioisotope thermoelectric generators that powered it using plutonium-238. And you can see on the right how, over the years,
so Fran, now I'm seeing you, not the slides.
That's
so after so when you showed the slides for the YouTube, that I saw, and then now I'm just seeing
yes, you need to click at the top where it says Fran Bagenal slides.
Oh, Fran Bagenal screen.
Yes.
Perfect. I see it. Sorry, my fault.
No, that's a common Zoom issue.
Sorry, I'm co-host and I did the common mistake. Go ahead.
So if you look at the power generated by this radioisotope nuclear power system, the watts have gone down almost half since launch in 77. But that's a long time. That's 50 years. But the real reason I'm showing this is that I am very worried that NASA is canceling, or the DOE is canceling the production of these plutonium up in Idaho. But if we don't produce these systems, these power systems, we won't be able to go beyond Jupiter. It'll be difficult. So if we want to go to Uranus, which is a high priority, we want to do interstellar probe, we have to keep producing these radioisotope power systems. And I strongly encourage people to advocate for maintaining the production of this material. Okay, politics. So next, I want to talk about some of the other technologies. What's very interesting is, of course, the computer capability that was available back then is minute compared with what we have available now. And so there was very limited computation available on board. There's a funny quote in The Farthest where Rick Terrell says, there's more computer capability in your pocket, and holds up a car fob, right, for a key fob for your car, and says there's more technology, more computer capability than on Voyager. The other thing that's really interesting is the storage was mag tape. And so magnetic tape was the way in which data was stored on board and then transmitted back to the Earth at 160 bits per second. it's still working 48 years later. Can you imagine that? It's just extraordinary. And so this old technology is amazing. Now, the instruments on board, there were the imaging instruments, which were ultraviolet spectrometer, imaging science, infrared, and the photopolarimeter was built here at LASP. These are all on a scan platform. And again, the farthest points out the difficulties of using this scan platform, particularly when one of them jammed up and they had to slowly move it around to get it released. So cool science, but from a shield and space physics viewpoint, well, we'll get to that in a minute. I mean, just mention something about the imaging. Back in the 70s, there was very limited capability in terms of how do you look at this stuff? It's downlinked images, and each flyby, you want to see them as fast as possible. And so this is some of the technology. And indeed, this was often what you saw. You would see something like the rings of Saturn with 3 different colors, and they'd be put together to make a color picture. I'm not watching the chat. So Marav, if there are chat comments, just call them out.
I will. You know, I need these slides. I so love all these images. Oh my God, amazing.
It's fun. But you see, the imaging people, they would see these pictures on a screen. They would maybe print them out and just sit around and talk about these images. But you had to be in the room, right? You couldn't send the images somewhere else. You had to be at JPL in the science lab, looking at the images as they came down, and then talking with your buddies about what are you seeing, what's going on, and so on and so forth. Very different from the modern era of doing science. And then also every morning, Ed Stone, who's here in the middle, would run a meeting of the science teams, and people would use these overhead projectors and project their data that they'd analyzed overnight onto the screen, and everybody would sit around and talk about them. And then Ed Stone would say, okay, you and you have got good stories. You can do your press conference. I want you to present at the press conference. And they'd go away and they would make slides, sort of little film slides that would be projected in the press conference, showing the data that they wanted to talk to the press. The press would then film this, and it would go into the newspapers and out on TV. In fact, I remember this beautiful image from March 1979 with Voyager 1. In fact, I remember taking this picture of the Great Red Spot and the dramatic stuff around it. Then it appeared on the front page of the New York Times the next day, except it was in black and white. Of course, because there was no color, but it was above the fold. It hit the front page above the fold, which was a big thing for science back then. Now, for particles and fields, I was involved in the Voyager plasma science instrument that was run by Herb Bridge at MIT, and him with Jim Sullivan, who did all the operational side of things. And on the right is a mock-up of the instrument that was actually, it's in the MIT museum, but you had 3 main Faraday cups that measured ions and electrons, ions, and then the side one, D cup, would measure the electrons. And this was that was the instrument, but the data would come down and we would get the data on mag tapes, and we analyzed, we just go to the mag tapes. These are the magnetic tapes that would be shipped overnight to MIT, and they'd be read and put onto the computer. And then we would process them. And we started off using these punch cards. And I happen to have some here in my office. You know, these are the punch cards left over. And you would sit at one of these tables. This was my first job as a grad student, and punch the cards, and if you made a mistake, you had to reject it and get another one in because you couldn't correct it. And then you had lines of code, and you would carry this box of punch cards over to the place where there was a computer, and that would be read into the computer, and you'd have your Fortran instructions about what you were going to do with the data. Read the data. You'd have the names of the tapes at the front, and then they'd load the tapes and read the data and analyze, and then and notice that there are lines drawn across the top of this box of tapes, right? And the reason why you need this line drawn across the top is in case you drop the box. Then you can put the cards back together in the right order, right? So this was 1970s, mid-70s technology with the mag tapes and the punch cards. And then the data would come out, analyzed, and you would get printout on a stack of paper. So here's an example. Let me just hold up. Leftover, these things would come, and they would come out and they'd go onto the printer. You can see in this image, and it would write come out, and you would then be given a set of printout that you could either text that would tell you something and said your code didn't work, you're going to have to do it again. This would be a 24-hour turnaround, by the way. So if you made a spelling mistake, you had to wait 24 hours to fix it. But also, if you told it to plot something, it would plot on the plotter, make your plots of the data. So let me tell you a little story. I worked on Voyager at Jupiter, the first flyby, and I was predicting what we would see. Now, the Io plasma torus, with Jupiter at the center and Io going around, produced a lot of plasma coming off Io. We didn't know why or how, but that's what we were going to find out. And you could observe from the ground using big telescopes. You could see the cold optical torus in close and the warm UV emitting torus further out. There had been some UV observations from Earth-based, Earth-orbiting satellites, and we knew that Voyager was going to have had a UV instrument too. Now, my qualifying exam was by hand to plot up what the papers were saying we should see. And I presented at a conference at UCLA. This is what Voyager will see. And there were those who were involved with either theoretical work or the Pioneer observations that Lou Frank had an instrument on Pioneer flying through. And they predicted very low density and quite hot. And then the ground-based optical people said it was going to be high density and cold. So what were we going to see? And my job was, as my qualifying exam, to go forward as a grad student, was to predict what we would see. And you can see these hand-plotted log plots here, where I drew this by hand and sketched up what we would see. So then the UV emission, the spacecraft approached Jupiter, and they were making observations, and they reported very high densities and quite cold. And we panicked that these high densities of different sulfur and oxygen ions would saturate the plasma instrument. So they carefully had a discussion and decided to come up with a compromise that changed their settings and so on. And this is what came off the plotter. Next one was that when we look at the low resolution, indeed, the data on the right from the A, B, C, D Faraday cups, different Faraday cups, were saturated, but in the high resolution mode, perfect data. And you can see, just as I had predicted, there were these multiple fingers of plasma, cold, dense plasma for the different ions. And so then my job was to take those data and fit these spectrograms, energy the measurements was reduced distribution function, or current was what was measured by the Faraday cups as a function of energy. And my job was to fit those with Maxwellians to work out the flow speed that they were all flowing with, what the density was, the temperature of these species. And so you fit these, you plot, you fit, you plot, fit them more, you check them, and you then collect all of the data in a binder. So if you can look at the picture of me, you can see this binder. And if you look behind me, there's a whole bookshelf of these binders. And, you know, I look at one of the, here we go. I plot them out and look at them. And, you know, sometimes the plotter didn't work very well. And sometimes it was a bit better, you know, and you fit them and say, nah, this doesn't look very good. Let me try a little different one, and so on and so forth. So classic graduate student job was to take the data and fit it to derive parameters, physical parameters that are telling you about the system. And that's standard job. And you compare, you see, does this make sense? Does this make sense? Does this make sense? Same thing now. It's just that we have better technology. It doesn't take as long to do that. But the bottom line was my predictions were validated and I got my PhD. Okay. So here's, you know, here we are, classic set of old 3-ring binders with all the data. Now, at the flybys, the teams would get together, different teams would all come together, and we'd hang out over by the plotters. Here's the plotter, and Chris Russell, Bill Kurth, and Fred Scarf waiting for data to come off the plotter and discuss it and see what you see. And then over here we've got Tom Comegis. He sort of looks kind of, he's lecturing and telling people, you know, how fabulous the LECP data are and how everybody else is wrong. Of course, Norm Ness is here looking at the MAG data, not showing it to other people and saying he's right and everyone else is wrong, you know, as these guys tended to do. And we got to look at the data. I want to also show you here, because this is kind of fun. The LASP instrument was the photopolarimetry, and we had people here from the University of Colorado, and what they're looking at the plots coming off, and what they did was they were looking at the data when Voyager went behind the rings and looked at a star through the rings, and then they made plots, and you can see here a long printout of the lines going up and down with absorption due to the rings, and then another little absorption, and you can see the microstructure of the rings plotted out in this long printout on from the photopolarimetry. And then also by Saturn, Ralph McNutt and Al Lazarus here have a plot. 3D plotting, woo! Very cool. And so you could get to see lighter ions and heavier ions as a function of energy, and hotter ions spread out, and then cooler ions, you see the very pointy, thin peaks. So this was at Saturn, looking for protons and heavies, the heavies coming from the moons, protons probably coming from the planet, and measuring density and temperature at Saturn. By the time we got to Saturn, the punch cards had been replaced with, we had keyboards, we had screens. Here we are at the MIT Plasma Lab. The equipment development lab equipment is in the back of the room, and us grad students were given computers to work on, and we stayed up late working away, looking at the plots and deciding if they were good enough or whether we had to make other ones, and so on. And then again, still hanging around at the flybys around the printouts, looking at the data and saying, what do you think? What do you think? Well, I think it's this. Oh, what we got here? What do we got? Usual story. A lot of fun. And then by the time we got to Uranus, we had color. I mean, color, plots, color, prints. Amazing. Completely different. We'd moved on.
Yes.
And then by 1989, at Neptune, we had the internet. Now, it was crude at first, but it allowed communication. You could do emails to colleagues. You could send some data, a little bit limited amount of data. You could send pictures, limited pictures, out to the press, out to the public. And they began to have public presentations live. You didn't have to wait for the TV to film and then show it on Newsnight. You could, or a documentary or something, you could actually watch the press conferences yourself and find out, via some kind of, you had to have access. So it was often phoning up. So you had to do a modem. The rates were very limited. So the quality was limited. But this was the beginning of a very different form of communication. You didn't have to be at the same institutions. You didn't all have to meet in a room. And so there was a way of distributing the effort, which made a big difference. You could consult with people across the globe and find out, well, what do you think this is? Or you wrote a paper on such and such. We've just got some observations. What do you think? How does this fit in? And all of that sort of stuff. It was a very different, it was much more, it wasn't 3 or 4 guys, literally, in a room deciding what was happening. You could bring in a larger group of people. The students could get more actively involved, and so on and so forth. There was a bit of a change in the climate of doing science. It was much less elite, where you had to be in the room, and you could be engaged and involved. So that made a big difference. So Voyager's out there, as you all know, out in the interstellar medium. Hopefully it will survive until 50th anniversary. The last thing I want to show you is a quick advertisement for my puzzles. These are wooden puzzles of planets. They're sort of 9 inches, and they're really cool, great holiday presents. Take a picture of the link, or maybe I'll put it in the chat, and go order them. The link's gonna go down on the November 14th, because they're going to be busy with their holiday puzzles. It may come back again, but go get the QR code or the link and go order some puzzles. And with that, I will stop sharing.
That was fantastic fun. You know that I go, I am an academic brat, so my both parents were academics. I remember going with my mom to the computer with the punch cards, and I just adore. I remember going JPL, seeing the old vax. I adore this. Yeah. I have a question for you, and we can open and folks, if you have questions for fun, please put in the chat or raise your hand. I'm just going to kickstart our conversation. I have a science question, but before that, I have a more philosophical one. That I wanted to hear what you think about it. Of course, you touched on an important point. Of course, when the technology evolve and you have emails and you have, the communication today is far different. the team is much more diverse. You don't have, like you alluded, like 3 or 4 guys, and if you're not part of the team, you cannot see the data, and it's much more democratic, and this is phenomenal for science. One thing I do though wonder is, or at least I notice that in my group when mentoring students, is the fast versus slow that is related with technology. And I know I came in a generation that we still went to library and read books, and I didn't rely on the internet at all. And I came before the first iPhones, and so I am used to thinking in a much slower way. I do like the paper. I do like printing papers because I read much slower. I slow down my brain when I'm reading in a paper versus in a screen. And I wonder, there is something about you're showing all these images that remind me of a slower pace, that you're in a room with other people, even though there is the flip side of lack of diversity, but you're having to discuss in a much slower pace. And
Right.
yeah,
No, I thoroughly agree. I think that um, having to digest material and understand it and think about it and you know, I think it's very hard to write a paper, which we have to do because we present our data via papers and so on. Learning how to write that, you've got to have read them, you know. And I worry if you just ask ChatGPT to write the paper for you. I mean, I understand how it helps with correcting language and making it readable and helping you look for sources. It's fine as an aid, but in actually sitting down and writing the paper, or reading a paper, you don't necessarily want it summarized in a few sentences. You got to do the work.
I also worry related with that is computer. You rely, a lot of the research is done, my own research like that rely a lot of computer codes, but if this is the only thing you have seen and you haven't done just a slow pace thinking, that even to say if the computer codes, they can be wrong, or even
Yep.
just the way that you have to
Yeah.
debate with, like, the line plots you show. Can you do a line plot that does not rely on a Python, on an ideal code, that just
Right.
still, if you understand the ideas, that is, yeah,
So it's all about DTMS. Does this make sense?
right.
And
I haven't seen this acronym, TDMS.
well, when I was teaching, when someone would fill in a homework problem and they'd get a garbage number, I would write DTMS question mark exclamation mark
Right.
exclamation mark on
Yes.
their homework, and they just 2 weeks into the semester they know what it means. It means,
Right.
does this make sense? Because if you write just a number, it doesn't make sense. If you haven't explained why it makes sense, right,
Yeah.
then they
Yeah.
don't get credit. Now, or doesn't make sense. If you produce a rubbish number, but you explain why you think it's rubbish, then I'll give you credit. Now, when doing, most of what we do with looking at data is you look at the data and you fit it in some way to
Yeah.
derive a physical quantity, whether it be plasma density or magnetic field or whatever it is you're looking for, wave particle interactions, structures, behaviors, temporal, spatial. Um, Again, you'll look at it and question, does it make sense? And so I spend a lot of time with my colleagues and students, not just the students, but also colleagues. Does this make sense? And say to them,
I agree, because a lot of, you can get from, for example, from codes, but I will imagine also, if you are not careful with the data, if it's an unexpected science, this
garbage
is
in, garbage out,
garbage out,
garbage
right?
in, garbage out.
Exactly. So if you are, you can, it's easy to use codes to reproduce what you expect. That's
Yes.
right. But the hardest part, if you really want to do new science, you really have to almost use it as a lab, and go back to see, is it
Twiddle this knob, twiddle that knob, twiddle this knob,
exactly,
twiddle that knob.
exactly.
Does it do what you expect it to do? Does it
Yeah,
make
so
sense?
coming back to your theme, the technology, I do I do like the old technology for that reason, that it slow you down, that it forced that there's something about the wave's brain in itself that you are forced to, not just write the first email. You really need to see it and to think before you're going to, you know,
Right. And or if you take something like a 3D MHD model,
right.
and then you look at the heliosphere and you're trying to model that, and you want to think about what happens if I change this parameter, that parameter. And then this is what you were talking about in your seminar. And then again, you have to look at what comes out of that model and check if it makes sense.
Right.
But the modern technology does allow you to make, looking at behind your head at the graphic on the wall behind you on your office, you couldn't make something like that back in the 70s. We didn't have the technology to do the modeling, and it's very powerful. But yes,
But in some sense, it was more creative. A lot of them, I think a lot of the fundamental papers came before the computers because of
yeah,
that. You had to really, yeah. I don't want to, I have a science question, but I see that there was somebody in the chat that had a question. Rebecca Jolitz, you want to unmute and ask your question, and then
Sure,
other
sure.
people. Yeah.
My question is more sciencey. Do you have any predictions for IMAP based on Voyager's observations?
you're asking the wrong person. Um, I work on planetary magnetospheres rather than the heliosphere. I follow a little bit about what's going on in the heliosphere. I know that there are a lot of predictions for IMAP based on Voyager, but I'm not the person to provide that. I suspect you guys are going to have a webinar on this topic before too long.
We should, yes, we absolutely should have that.
Yeah.
Rebecca, this is something we were been thinking to do it. We are going to do a webinar. We were going to do it within Shield of Science, but we should open up for to have discussion. I can just tell you just a taste of it, Rebecca. One of the beauty of Voyager that, when you're looking at microphysics like turbulence or connection or particle acceleration, you want to have something like Voyager, like going in situ data. All these peaks that Fran is showing, you need right there to have the in situ. The ENA measurements are fabulous, but there are lines of sight integration, so you don't know where the phenomena is coming. So they're both fantastic because the IMAP is going to get 3D and it's going to show the heliosphere probably breathing in and out and flickering. It's going to be fabulous. But I think we will have to go back to Voyager data to see if it makes sense, whatever theories we will come up to explain IMAP. But I'm making a note. I know Justine is on the call, our project manager. We will take upon to have a webinar open to have this discussion. It's a fabulous idea. I have different science questions, Fran. You showed the high resolution data versus the low resolution from PLS. I haven't seen it because I'm used to seeing the John's plots that he struggled with the D cup, the B cup, and in low res. How did you guys do it to high res?
Well, the energy range is the same from 10 volts to 6 kilovolts. And it's the number of bins in energy per charge that you separate out. And the advantage of the low resolution is if you've got a very weak signal, you can then get enough counts.
No, that I got,
Current.
but how did you had to reprogram Voyager? I'm just trying to
No. It's always it only has two modes. They're called low and medium, M mode and L mode. I think there was probably planned a high resolution mode that never happened. But since launch, it's had the H mode and the low and high, and
I haven't seen John discuss the M mode on the L mode. I wonder for the
Well,
helios, did he make
in
use
the
of it
outer heliosphere, the fluxes are so low,
that
they
he,
may
right?
have to only use the low resolution mode to
This
get
is what the data,
signal.
he does a heroic thing to try to get fitted with,
Yeah.
but it's probably he's using one mode. I haven't seen him
Yeah.
discussing these two.
What's
Nick,
the
you
other
have a question?
advantage of
Howard, sorry.
the high resolution one is allows you to separate out the fingers of a very high Mach number flow. Then you've got these separate species. So in the solar wind, you want to use high resolution so you can actually get that fast moving cold
No, that I got. I
ion.
was just wondering. It's probably because the signal is so low
Yes.
that John.
Yeah.
Yeah, that's
Yeah.
probably what it is.
Right.
Howard, you had the question, and I think Nick has also a question. Yeah.
Yeah, thank you very
Hi, Howard.
much. Hi, and thank you, Fran, for such a great talk and how technology evolved to help us to better understand the data that we're getting back from the satellites. I have a sciencey question, and that is, you talked about your prediction for the densities and temperatures and so on in the Io Taurus, and how the Voyager data showed that you were right. What data or insight or information led you to be able to predict what was observed?
So there's various ones. One was Pioneers. So the Pioneers flew through in 73, 74, and Lou Frank's instrument. I mean, you got to remember the Pioneers were carrying 1960s plasma instruments. It was very old. And they flew through not exactly the center of the torus, and they made predictions at this conference and said it's 100 per cc, it's protons, and it's 100 eV. And they said that's what it was, and we flew through it, and this is what it is. Now, it turns out that if you look from the ground with a telescope, and in fact, this was how the Eoplasma torus was detected. The radio emission was detected back in the mid-50s, but looking at the emission from the torus came from using visible light, and they could see S plus emission. And everyone was like, what? S plus in a ring around Io? Where does that come from? Everyone was struggling with trying to understand it. And then there were a few UV observations with rockets and early satellites, IUE, I think it was called, UV, that was detected maybe S double plus and O plus ions, and that they were hotter and denser. And so what was going on? And of course, so when we got there, I did my predictions based on these ground-based observations and what we had for UV observations. And then, of course, the beauty is we flew right through, and we went from a warm region where the peaks were merged together in a single, added together all the sulfur and oxygen ions together. And then it cooled down as we went inside Eo's orbit, and these fingers began to appear, the separate cold multiple species. You could resolve them. And so we flew through from the warm plasma torus that emits in the UV into the cold plasma torus that emits in the visible. And so that was pulling together those observations from different viewpoints.
Good.
Yeah.
Thank you.
I know Nick has a question, but I just wanted to, before passing to Nick, Fran, just to come back to the topic of technology and what we're discussing, do you have, I don't know, maybe a suggestion of how we can make, when we have workshops, for example, or New Horizons, or if we had the swim workshop in the summer, if there is a way, I think a lot about it, how to provoke better discussions like you're showing people hovering over the one plot in one room to have that intellectual discussion. We were just chatting the other day, and I said how much EC meetings are phenomenal for me. even though they're not by invitation and there is all these other problems. And so we don't like that. But I still, there is something that is very tricky to have in the same room, to have an scientists that are guarded as people, but to have people conducive to be really in-depth discussion. I don't know if you have thoughts about it.
So I like Chapman conferences. They're more like 100, I
Mhm.
think, or 50.
Yeah.
And I think GEM has some very nice discussions, and SHINE and so on. What I've been doing, and the Magnetospheres of the Outer Planets, MOP, which is a sort of a
Yeah.
just ad hoc group of people that's been meeting for decades now, every other year. What I've been doing when I run a meeting like this, is sometimes to have someone who can prod the audience at a discussion time. So one of the things I've often done is said, okay, let's pretend I'm the Jupiter fairy, and can give you some information. What information would you love to know about the system, say the Jupiter system? Or I'm a heliospheric fairy. What would you love to know about the heliosphere?
Mhm.
Or you could be very specific about this boundary layer between here and here. What would you like to measure or know? What are the numbers that you would like to know about that boundary layer? And that provokes a discussion about the physics of what's going on and how you might take this observation and that observation, or what the future observations you would like to make. So I think
That is a great idea. Yeah.
I think the other one I think I'd like to mention is George Sisko at the summer schools, and I wonder if Nick remembers this. The summer schools we had, the heliophysics summer schools, he would often, when there was someone giving a talk and it was getting very technical,
Yeah.
he would say, could you give me a push-pull explanation of how that works?
Right.
And that was really useful, because if you can't give a push-pull explanation, then you don't understand it. But the equations are beautiful, they're lovely, and they're very powerful. But you've got to be able to stand back and say, how does this work? What is causing what to do what? And that's very important, not
Yeah.
just for communication, but also understanding.
Right. Yeah. That is right. It's a really good suggestions. Yeah, about that. Nick, you had a question, and I see Larry also, one of the two, want to unmute.
Why don't you go to Larry first?
Okay, Larry.
Actually, mine was just an answer. I was just pointing out that the PDS, which I was fortunate enough to be a member of the original PPDS, was starting not just a couple of years after the Saturn encounters, and by the Uranus and Neptune encounters, we were actually shipping data on CD recordable disks with the PDS metadata. So people were asking, what did you do before the internet?
Right. Yeah. So the idea, we had mag tape shipped to us from JPL,
Yeah.
and the different teams had got their mag tapes. But this issue of ordering disks to get the public, and of course, there's the whole value of the PDS is making the data public and available. I know, that's interesting.
Yeah, I know you guys
Yeah.
are working on that. That is, yeah.
CDs. I don't think I've got a CD in my room. I've got a lot of old pieces of stuff that I keep, but I don't have a CD.
That's odd. That
They're
is-
like this, right?
Yeah. We were talking the other day about the difference. Oh, actually, it was me. He was driving me back, and we were talking about the difference between CDs and records, LPs,
Yeah.
and how, in LPs, the warmer the voice. Nick, you want to ask a question for Fran?
Yeah, I was just thinking about like some of the discussions about like when to release data and making data open. What is that when you're going from like only the people in the room get to like look at the data, and then you're like gonna put it all out you're gonna transfer it all onto the web? what do you remember if there was a discussion about that? Was there a debate about that, or any concerns about making that data available in that way?
So it's funny. I actually blame the climate scientists, because this climate denying scientists are the ones who really forced public release of data very quickly, because they were like, it's not true, it's lies, you're making it up. And so show us the data. And so the climate change people actually had to release the data and make it public. And that was good to some extent, because you made the data public and people could look at it and say, yeah, the climate temperature is going up. You can't deny it. On the other hand, what that has meant for space science is that you're supposed to release within a certain amount of months, make your data public and available. And the two things against that, it's nice that everybody can access the data, but the disadvantage is that if you have some doubts about the data, like understanding the noise, understanding uncertainties, understanding how the calibrations, understanding, there are various issues associated with data processing that are not simple. It takes work. It's not, exactly. So that's a concern, that you put the data out and it isn't necessarily going to be perfect and it's going to take some work. The other problem is you're then making the data public for people, and it means that if, particularly for, say, junior scientists, need the time to digest it and understand it and write it up and get it published and get credit. Whereas if you have to push it out immediately, then someone else can pick it up and run off with it and misinterpret it or interpret it and make new results, just ahead when someone else hasn't quite got their paper out yet. So it puts a lot of pressure on people to publish immediately, which is not necessarily healthy when you need to sit down and talk about the data.
Oh, yeah, I agree. And the other, right, I remember when I came to the Nick on the Voyager teams, and especially I was blown away I'm still blown away. When you look at the magnetic data, it's at the noise level. The magnetic field in the helio sheets is 0.1 nanotesla. The noise is 0.05. And depending on the components, it's deep down the noise. And Lemberlager, the care. I was the image I had was a Swiss watchmaker. He will look at every wiggle, and the care to really say which one he agreed or didn't agree. I love that care. So I think it's a great public release, but I do like the humility that Fran is talking, just to make sure that even the data is as noisy as, especially when it's a new data in a new area. If you don't know what you're doing in the background, it's really, really right.
Yeah.
I think the humility is a big, yeah. I see that
Rebecca has a good question.
yeah. What is
She asked about, she
the
says,
Viking, right?
yeah, she says, are there
Rebecca,
any,
you want to ask?
yeah, do you want to ask, Rebecca?
Unmute.
No, there's nothing I'd add to it. Just are there efforts to digitize raw paper from early days? Because there's been data lossages that have occurred for other missions. Like Viking, there was a fire in the facility
I didn't
where
know
some of the
that.
data was
Wow.
being, I was talking to Chris McKay when he was trying to help out with some efforts, and they were literally reaching out to the scientists who were on the team to try to digitize, get back those records.
Yeah, we've actually got got a storage cabinet with a whole bunch of stuff that I'd be meaning to get round to digitizing and haven't done. But anyway, yes and no. I'm a bit torn here because I've been going back and redoing. I got a PDOT to reanalyze Voyager data and make it available and public in easily analyzed from the different magnetospheres, and we've been doing that for Jupiter, Uranus, Neptune. I'm hesitant about Saturn because I'm thinking, we had Cassini that was in orbit. We got all this extra data. Why bother to go back and reanalyze the Voyager data? You can see both sides to that. On the other hand, if you expect there to have been temporal variability,
Right.
then you
need
do
Voyager.
want to, right?
Right.
So the value, for example, of New Horizons is that it's flying through the environment that Voyager flew through, more or less. And it's, I don't know, 15 years later or whatever it is, different phase of the solar cycle and with different instruments, but you're getting to see temporal variability over the cycle and looking at things a little differently. So
I think, Fran, solar wind is going to change in Saturn. It's going to
Yeah.
drive the system. I think will be amazing.
yeah, so yes, I think it is worthwhile. I don't know about Viking specifically. Maybe a little too old.
Yeah, Viking is the one where, because those contaminants from the organics pyrolysis became a matter of discussion in terms of once we had the perchlorate in the picture, then everybody wanted to go back to it.
Yes. Yeah, that's interesting. I didn't know that they had a fire.
I wanted to, we only have 5 more minutes, and I know that there is some people in my group, the younger generation, in attending. Do you guys have any questions? Don't be shy to ask Fran about how was it in the Voyager in the old days or whatever. I won't call you guys by names, but you know who you are. Oh, Eric, go.
Hi, Fran. That was really cool to see the history. I was just wondering, do you think missions today don't have the same sort of change in technology? Like missions today, they're going to be 40 years old. I don't expect them to have so much change, right?
Well, I think there will be change. The big changes that are happening, one is making stuff lighter, right, and faster. And so that's amazing that you've got these small instruments, very sensitive, but also the lightweight, ability to build things light and the computer capability on board. Now, this is something that's very important and highly relevant for SHIELD. I think what we need to do is to develop some small sats that we send out away from Earth, out into the heliosphere, and we do onboard data processing, right? Because if you think about it, you're measuring the solar wind, you're measuring cosmic rays, something, whatever it is you want to measure, you can analyze those data, and a lot of it is not particularly exciting. And you can do some onboard data processing, and then you hit an area where you get a lot of variability, and you can, store a lot more data, and you can store it online. So what I'm thinking is one of the biggest issues is communication. Communication is a big deal. It's power, communication, are the two, and propulsion are the 3 big things of space science. So with communication, rather than send everything back all the time, if you have onboard data processing with some sort of intelligence in your onboard data processing, it can then say, okay, we'll send all of this, or we'll just send the average. And then you can always send up instructions saying, well, actually, we do want to have the lower resolution as well. But you store it all on board. I mean, not using mag tapes.
You know what we need to do, Fran? I've been part of a meeting called KISS in Caltech that was thinking about that.
Yes.
We need to redo it again with a new
Yes.
generation, and
Right.
SHIELD has a new generation, new ideas, and look at this problem. It's a fantastic thing.
Yeah.
Eric, KISS
there's a lot of
workshop.
good stuff. Now, the only problem is the instrumentalists, they want every single piece of data down, rather than have onboard data processing. But I'm sorry, if you want the quantity and quality of data that you would get this way, then you'd have to do onboard data processing. The other thing is, communication is tough, but we can make the ears on the ground bigger. Like the DSN should be quadrupled. We should make it 10 times the size and listen to distant satellites that we're sending out into the outer solar system and beyond, right?
I agree. DSN is a bottleneck and needs to completely be expanded.
Right.
I agree. I agree with that. Fran, this was such a delight. we are top of the hour. We need to finish. That
Okay.
was incredible. Thank you. Thank you for that. And thank you, seeing you again.
Look forward to the next seminar.
I know. You
Right.
you gave,
Right.
yeah, fabulous folks.
See you
Bye.
folks. Bye.